Hi everyone, thank you so much for joining me today. Today we are focusing on grade 11 functions, and functions are of course a huge part of your paper 1 exam. They come up in many marks. Okay, so there's different types of functions, of course. We learn about the straight line back in grade 9, and of course we build on that knowledge. We learn about parabolas, which we also call the quadratic function. We also learn about hyperbole, and we learn about the exponential function. And then we also add things like the inverse and all of that, and we build on our knowledge of functions, and it keeps growing. The functions that you know now, you are just going to keep on building on. If you go on to study maths or any type of maths course in university level or technical school or wherever it might be, you will certainly add on to the functions that you're learning about now at school. So we're going to start with the most common function that you do in grade 11 tests and exams. Most of your marks are based on these functions, and that's of course the quadratic function. So let's remind ourselves what the equation of a quadratic function is. So the equation is y is equal to ax squared plus bx plus c. A, b, and c values are either given to you or you'll have to find them. C is the y-intercept of the graph. The value of A affects the shape of the graph. Now what that means is if you've got a negative coefficient of x squared, so say this is negative x squared here, then your graph is going to do this. We say if A is negative, then the graph has maximum problems and it's really a sad face. So this is often what we say, sad face. It's an easy way to remember what the graph's going to look like. So if A, for example, was -1, you're going to get a graph with a maximum turning point that looks like it's quite sad because it's got maximum problems. And then if A is, say, +1, for example, so if A is greater than 0, you're going to get a graph that's happy because it's got minimum problems. So in other words, it's got a minimum turning points. Okay, so that's just a nice fun way for you to remember smiley face and sad face. That's a nice way to remember, and an easy way to remember what the shape of the graph will be depending on what the value of A is. One of the important things you learn about a quadratic function or a parabola is that the graph is symmetrical about the axis of symmetry. The coordinates, or the value rather, the equation of the axis of symmetry is given by x is equal to -b over 2a. When you use this formula, always use brackets on the value of b so that you do not mix your signs up. Now, what an axis of symmetry does is it divides the graph perfectly so that if you fold it on top of itself, you basically get the exact same graph. So you cannot tell the difference between when the graph is reflected in the axis of symmetry or when it hasn't been reflected in the axis of symmetry. You get the same graph, okay? So anything that's symmetrical about an axis of symmetry will give you the exact same shape, all right, and the exact same graph. This, remember, will give you the equation of your axis of symmetry of a parabola or a quadratic function. Now, another way that we could be given the standard form of a quadratic function is as y is equal to a into x plus p squared plus q. This is what we call the turning point form. The reason we call it the turning point form, guys, is when you're given a graph in this form, you don't have to do any work to work out the turning point. The turning point is already there. It's simply the negative value of whatever p is. So if p was positive, it will be negative. If p was negative, it would be positive. So it's negative p, and q will give you the coordinates of the turning point of your parabola. So please, if you've got a graph given to you, say for example like this, x plus 3 squared plus 2. Do not times this out and then go and find the axis of symmetry and then substitute that value in to find the value of the y part of the turning point. There's no need to do any further work. You simply read off the coordinates of the turning point straight from the turning point form of the graph. So therefore your turning point, the coordinates would be, change the sign, so it would be -3 and 2. Okay, we read it straight off from what they gave us. Remember, when you're given the axis of symmetry and you've got this form, the standard form of the quadratic function, you've got to do a bit of work to work out the turning point. You first find your axis of symmetry, which is the x value of your turning point, you then take that value and you substitute in place of x and then work out what the y value of the turning point is. In the turning point form, as I said yet again, the axis of symmetry, which is the x value of the turning point, is simply given by x is equal to negative p. All right, the y value is already given to you in your equation, so do not do further working out on that equation. Now, when you sketch the parabola, there's some important things to remember. The sine of A determines the shape of the graph. We've already spoken about that. So your graph can either have a maximum turning point or a minimum turning point. The value of A will tell you whether your graph's going to have this shape or that shape. You also need to find the turning point. If you've been given the graph in standard form, you've got to first find out your axis of symmetry and then resubstitute to find the y value of the turning point. And then you need to find the x-intercept by letting y equal 0. So this is where the graph will cut the x-axis. Or you find the y-intercept by letting x equal 0, which is where the graph will cut the y-axis. All right, so these are the few steps and points that you need to be able to sketch a parabola. You need to know what the shape is, you need to know what the coordinates of the turning point are, and you need to know what the coordinates of the x-intercepts and y-intercepts are. Now, when we're talking about a parabola, while we're still on this, your x-intercepts, at most, you will have 2 x-intercepts. That's where they cut, where the graph cuts the x-axis. You might have a case, guys, where you have a graph that's actually turning on the x-axis. Okay, so it's sitting on the x-axis. In that case, you will have your turning point and your x-intercept as the same value. So you might end up with something like, say, x minus 1 squared is the equation of the parabola. All right, so you only then have essentially one x-intercept because that value is squared. Okay, now often we will ask you to find the equation of the quadratic function. There's different things and different ways that you can find the equation depending on what you've been given. Traditionally, there are 2 ways that you can be asked to find the equation. Either you're given the x-intercepts and a point, or you're given the turning point and a point. This can change. It all depends on your equations and the information you've been given. But the general format is we'll give you the x-intercepts and a point and ask you to find the equation, or we'll give you the turning point and a point and ask you to find the equation. So what do? If you are given the x-intercepts and a point, and you are asked to find the equation, we use what we call the factorized form of the general form of the quadratic function. So y is equal to a times x minus x1 times x minus x2. x1 and x2 are the values of the x-intercepts that you were given. And then to find the value of a, what you would do is you would substitute the other point that you've been given. So whatever you were given, say you were given the point 1, 2 lies on this graph. You will substitute x as 1 and y as 2, and then solve for a to work out the value of a, which you can then put back into this equation with the x-intercepts and then find the equation of the parabola. Importantly, you must write the quadratic function in the form it was requested. So if no form is specified, you can give it either in standard form, which is ax squared plus bx plus c, or you can write it in turning point form, which is a times x minus p, x plus p squared plus q. Okay, if you were given the turning point now and another point, what you would do is you'll start by substituting the turning point in for p and q, and then substitute your other value for x and y and work out the value for a. So in this case, if you are given the turning point and a point, do not use that other form. Don't use this one to find the equation of the parabola. You can, but it's going to take you long. Rather go straight into using the turning point form of the quadratic function to help you find the value of a by substituting turning point in and the point that you were given. Now, I want to quickly look at an example. I'm not going to work this example out. I just want to show you what I'm talking about. So in this example, I've been given the turning point is 1 and 5, and I've got the y-intercept is 0 and 3. So I'm not going to now go and use ax squared plus bx plus c. No. All I'm going to do is I'm going to say y is equal to a times x plus p squared plus q. I don't know what A is, so I need to find that. So I'm going to leave A there. I'll put P in as -1. Remember, you change the sign. And Q is 5. And then to find the value of A, all I will do is substitute that value for X in as 0 and Y as 3, and then solve this equation out to find the value of A. Once you get the value of A, you will take that value of A, resubstitute into this line with Y on the left-hand side, and then you will get the equation of this parabola in turning point form. Now, if they said to you, write the graph in, or write the equation of the graph in standard form, what you would need to do is take that value of A, put it back into your turning point form, so substitute that value of A back in, and then multiply out your brackets so that you can rewrite your equation in the form ax squared plus bx plus c. Okay, but if they haven't said anything, then you can certainly leave your answer in this turning point form. All right, guys, so just some important concepts that we saw. When we're given the x-intercepts, you know that you use y is equal to a times x minus x1 times x minus x2. And then if you're given the turning point, you're going to use the formula y is equal to a into x plus p squared plus q to work out the equation of your quadratic function. Okay, so think about all of that and apply all of that when you are faced with finding the equation of a quadratic function in your tests or exams, and when you practice your questions as well. Get used to using the correct formulae. All right, let's take a quick break. When we come back, we're going to talk about another very important function that you will use again in grade 12, and that is the exponential function. Hello, welcome back. We are looking at revising functions in grade 11 today, and so far we've looked at the quadratic function. Now we're going to turn our attention to the exponential function, an extremely important function because it models growth, yes, of course, as well, and because you're going to come across it again in grade 12 when you look at inverses. So what is an exponential function? Well, it's defined by the equation y is equal to a times b to the power x plus p plus q. Okay, so that's just the standard form that you've got to remember when you are working out the equation of an exponential function. B is, of course, the base. A is the coefficient of whatever the base is. X plus p, that's the power. And then q is whatever shift we are getting on the vertical side, which we're going to look at just now. Importantly, the value of b cannot be equal to 1 because we're talking about an exponential function. If the value of b is 1, we will get a non-existent exponential function. B has to be positive. So what I want to do is, instead of writing down a whole lot of notes on what A does, what B does, and what Q does, I think it will be a lot better if I show you what they do. So I've got a graph set up for you where we're going to move the values of A, B, and Q around and see how the function behaves. Let's have a look at that. All right. So in blue, you've got the graph f of x is equal to 2 to the power of x. Okay. Now, as you can see, the value of a at this point is just equal to 1. Remember, a is the coefficient, as you can see. A is the coefficient of this exponential function. We've done nothing to this exponential function at the moment. It's just the ordinary graph. Y is equal to 2 to the power of x. Okay, look at what happens to the graph as I make the value of a bigger. So that means increase it in a positive direction. So at the moment, a is equal to 1. If we start making a bigger, so let's say 2.1, for example, do you see that the incline of the graph is actually changing? So if I make the value f of x is equal to now 2,1 times 2 to the power of x, the graph you can see is becoming steeper, so it's increasing at a faster rate. All right, and if we take it all the way to 5, you can see that the graph is now a lot steeper. Okay, so the value of a, you can see, will affect the value, the steepness of the graph. If I start now making a smaller and start making a negative, what happens to the graph? Well, let's do that. So if I now take a into a negative, so look at what was happening. As a was getting smaller, the graph was getting more shallow. But now if I turn a, obviously 0 just gives you the x-axis. if I make a, let's make it 0, 5, negative 0, 5. Do you see that now your function has indeed reflected itself in the x-axis? Positive y's become negative, negative y's become positive when we reflect in the x-axis. So therefore your graph has now turned itself around and in fact has reflected itself in the x-axis when the value of a is negative. So your graph literally flips over. All right, so if I were to make a more negative, you will see what happens to the graph there. Okay, so a negative value of a is a reflection in the x-axis. All right, let's take a back to 1. Okay, hopefully all of you can now see what the value of a does to the graph. So let's leave a as 1. So we've got now again the function f of x is equal to 2 to the power of x. And let's play around with the base. Okay, remember your base can only be positive numbers. There cannot be negative values for your base. Let's look at what happens as we make the value of b bigger. So again, you can see the graph is getting steeper. All right, and as we said, b cannot be negative, so we're not even going to try that. But look at what happens when b becomes a fraction. Have a look. So we're going to be taking it into a common fraction. There we go. So at this point, we now have a value for b between 0 and 1. That's where all your common fractions lie. So if we take, for example, b is equal to, if I can get it there, just move it slowly, and b is equal to 0, 5. So we started off with y was equal to 2 to the x. We're now looking at the graph of y is equal to 1/2 to the power of x. You can see that that is a reflection of the graph y is equal to 2 to the power of x in the y-axis. So that's a reflection of the graph. We've now gone from an increasing function to a decreasing function because the value of the base is a fraction. All right. And let's take b back to what it was before, which was 2. And let's look at what the value of q does to the graph. Now, you should all remember what the value of q does to any function. It moves the graph vertically upwards or downwards by the value of q. So let's make q a positive number. And do you see your graph moving up? So if q is equal to 3, the graph of, there we go. All right, or even, it doesn't matter, it doesn't have to be a whole number. But if we make q equal to 3, you can see the graph of 2x has literally moved up the y-axis by 3 units. How do we see that? Well, originally the y-intercept was 1. Now look at the y-intercept. It's 4. It's moved up by 3 units. If we were to make q negative, of course the graph is then going to move downward by q units. All right, so if we have a look there, the graph has now moved off your screen 5 units down the y-axis. So q affects the vertical movement of the graph. And you can certainly change all the values together and see what will happen to the graph. All right, so guys, we've looked at what the effects of a, b, and q are on the function. It's always easier to visualize these things instead of just talking about them. Hopefully you now have a better understanding of how a, b, and q affect the exponential function. But what about the value of p? All right, so now let's talk about the value of p. We're going to talk about that, in fact, just now. Let's just mention one more thing about the value of q. Remember that your exponential function will have a horizontal asymptote. An asymptote is the value of the graph, a value where the graph does not exist. So if I take, for example, y is equal to 2 to the power of x, which is the one we were exploring with, you can see that the x-axis, which is the line y is equal to 0, is a horizontal asymptote. While we're talking about this, importantly, if we ask you in an exam or a test to state the equation of the asymptote, do not say horizontal asymptote is 0. Or do not say vertical asymptote is 0, or whatever the case is, depending on what graph you've got. If we've asked you for the equation, you need to give the equation. So the horizontal asymptote of the exponential function y is equal to a times b to the x plus p plus q is y is equal to q. In this case, y is equal to 2 to the x plus 0, so therefore y is equal to 0 is the asymptote of the exponential function. If the value of q here was 2, then y is equal to 2 would be the equation of the asymptote of the function. If the value of a is positive, your graph is going to lie above your asymptote. And if the value of a is negative, so as I showed you before when we reflected this graph, then your graph will lie below whatever the asymptote is. Okay, now let's talk about the effect of p very quickly because it is important. Just like in every other function, p is a horizontal movement of the graph. Obviously, it depends on what your defining equation is. Generally, in our defining equations in grade 12, p represents a horizontal shift. So the effect of p is a horizontal shift on the exponential function which we've been working with, which is b to the power x plus p. So what happens? Well, basically, all the points on the graph will move the same distance in the same direction. So the graph shifts either to the left or the right, depending on what the value is. If the value of p is positive, and this is very important, if the value, so say we've got 2 to the power x plus 2. This value of p is positive. The graph does the opposite to what you think it's going to do. It's not going to move to the right. The graph will move 2 units to the left. So even though this is a positive 2, the graph moves 2 units to the left, and when you substitute values for x here, you understand why the graph is actually moving to the left and not to the right. If p is negative, so say we have 2 to the power x minus 2, the graph will move in the opposite direction. The graph now moves to the right, so it moves away from the negative numbers. So let's have a look at what that looks like. So if we've got an original function here given by f of x, which is, let's say, 2 to the power of x, all right. Now you'll see the graph that's moved to the right. What was the value of p there? Well, look at what's happened to the x values in each case. In this case, we've gone from 2 to 5, so we've added 3. We've gone from 1 to 4, we've added 3. From 0 to 3, we've added 3. So this graph here in red is 2 to the power x plus 3. All right, this is 2 to the power x minus 3, exactly the point we've been trying to get at. So the graph does the opposite of what we think it's going to do. So this is 2 to the power x minus 3, where your graph has moved 3 units to the right. Okay, similarly, if you look at your other graph in blue, you will see that all your points, we've gone from 0 to minus 2. So we've moved 2 units to the left. So here we've gone from 1 to minus 1, from 2 to 0, 2 units to the left, and so 2 units in that direction would mean that our graph is 2 to the power x plus 2. So the graph's moved to the left, which means that the value of p must have been positive 2. The graph has moved to the right, so the value of p must have been negative 3. All right, remember the graph does whatever you think it's going to do, it does the opposite of that. Why? Well, if you substitute values in, you understand why that is. So if we look at 2 to the power x minus 3, if x is 5, right, we get 2 to the power 5 minus 3, which is 2 to the power 2. 2 squared gives me 4. All right, and similarly, you can test points on 2 to the power x plus 2. All right, so the key things we've seen here, we've seen how the value of a reflects the graph if it's negative in the x-axis. We've seen how the value of b, if it's a fraction, will give us a decreasing function, and if it's a whole number, will give us an increasing function. We've also seen that q moves the graphs vertically and p moves your graph horizontally. All right, so that was just a quick summary of all of the important concepts on quadratic functions and exponential functions. Remember to apply these when you start looking at your practice and start practicing questions. Next time, join us for more questions on functions. Thanks for joining us, grade 11s. Cheers.